Structure and physical properties of carboxylic acid and its derivatives. Here is the general structure for carbonyl compounds or carboxylic acid derivatives. The carbonyl carbon is sp2 hybridized here. So this carbon right here is sp2 hybridized. And it's going to use 3 sp2 hybridized orbitals to form 3 sigma bonds, one with the alpha carbon. So this carbon right here is an alpha carbon, and another one with the carbonyl oxygen, and another one with the substituent Y. All of these bonds right here are sigma bonds. So sigma bond, sigma bond, sigma bond. Out of these 2 bonds, one will be a sigma bond and the other one would be a pi bond. We'll talk about the pi bond in a bit. And all of these atoms, the alpha carbon, oxygen, and as well as the substituent, they're all going to lie in one plane, and the bond angle here will be 120 degrees. The carbonyl oxygen is also sp2 hybridized. So this is also sp2 hybridized. It's going to use one of its sp2 orbitals to form a sigma bond with the carbonyl carbon. And the other 2 sp2 orbitals contains the lone pair. So here are the lone pairs. The remaining p orbitals that is present on carbon and as well as oxygen, they are going to overlap together to form a pi bond. So out of this double bond, one is going to be a sigma bond and the other one will be a pi bond. Esters, carboxylic acids, and amides, they all have 2 resonance contributors. The one on the left are the ones which is going to be a significant contributor. The one on the right, they have a positive charge on the heteroatom. So in all of this, you can see that there is a positive charge. Now, when you compare the stabilities of all of these 3 resonance contributors of these 3 different compounds, you can definitely say that this is the one that contributes more towards resonance hybrid because it has got a positive charge on the comparative less electronegative nitrogen. These 2 structures, they have a positive charge on the most electronegative oxygen atom, and therefore they are considerably unstable. Or we can consider them to be insignificant contributors. Here is the relative boiling points of the different carboxylic acid derivatives. Esters, acid chloride, and ketones and aldehydes, they have about the same boiling points for similar molecular weight, but they are considerably lower than what we see in the case of alcohols. Alcohols have higher boiling point because of hydrogen bonding. And also, when you compare these carboxylic acid derivatives with that of amide, carboxylic acid, and nitriles, all of these 3 compounds are going to have higher boiling points. And this is because of the 2 important effects. One is dipole-dipole interactions, and the other one is hydrogen bonding. For example, when you consider nitrile is going to have strong dipole-dipole interactions, because of which its boiling point is close to that of the boiling point of alcohol. And in the case of carboxylic acids, we know that the carboxylic acids normally exist as dimer because it has the ability to form 2 hydrogen bonds between them. Therefore, it has a very high boiling point. And then when it comes to amides are the ones which have very strong dipole-dipole interactions. In fact, if you're going to take an unsubstituted amide which has 2 hydrogens here, this is going to have extensive hydrogen bonding with the other molecules, basically intermolecular hydrogen bonding, and because of which they're going to have very high boiling points. Here in this case of ethanamide, it has a boiling point of 221 degrees Celsius.